Fuel control, emissions, and sensors. This is really geared toward gasoline engines, which is what we're really covering here. Uh, Diesel engines do not use fuel control as we know it. It's very different. And even though diesels will use air fuel ratio sensors, they use them for a different purpose and they're used very differently. So everything I'm going to talk about here is really about gasoline engines. And I'm going to talk about, and I put this PowerPoint up in the on the canvas. So I opened the page with this PowerPoint presentation. There's a lot of notes in here, as well as I have some animations and other stuff. I also have all the slides for Lambda in here and the Lambda calculator in here. I'm not going to go over them again because we already kind of went over those, but they are in this presentation also. So I'm going to talk about air fuel ratio and its effect on emissions. I'm going to dial that in a little bit more. I think the book's overly vague, largely because they're looking at things on a national level, where in California, we really look at them much more on a local level, because in California, we really do care about those emissions and we have to fix them, unlike Kansas, that it's a non-issue for them because they don't enforce any of that and they're not trying to fix it. So we already talked about Lambda in the previous presentation, but it is in this PowerPoint. And then I'm going to get into oxygen sensors. And there's three different kinds of oxygen sensors we use on cars: zirconia, titania, and air fuel ratio, or called a wideband sensor. And we'll talk about why we use those. We'll also get in and discover that a zirconia sensor is really not an oxygen sensor. It's a lambda sensor. Just like the air fuel ratio sensors are a lambda sensor, they're just able to operate at a much wider range. And kind of cover what I mean by that, a much greater air fuel ratio. So the air fuel ratio is the amount of air primarily made of nitrogen and oxygen compared to the amount of fuel for which the purpose is, this discussion is gasoline, which is a hydrocarbon. The ideal air fuel ratio for gasoline is 14.71 pounds of air for every pound of fuel, which is normally displayed as 14.7 to 1. And so I showed you this chart before, where we got our hydrocarbons, which is our fuel, and then our air, which is also fuel. Don't forget, I need the oxygen in the air. That's part of my fuel chemistry. And I'm going to combine my hydrocarbon, my hydrogen with oxygen to make water. I have some fuel that may come out the tailpipe unchanged, which will be a hydrocarbon, that's unburned gas. In a perfect world, I'm going to add my carbon to my oxygen and make CO2, carbon dioxide. That's what I want. That's my efficiency gas. However, I may be unsuccessful. I may be running slightly rich or not have enough oxygen atoms, in which case I'll make carbon monoxide, or CO, which is due to a lack of oxygen. If I'm running too lean, I'll have excessive oxygen coming out the tailpipe. If I'm running too rich, I don't have enough oxygen to oxidize my carbon and make water. So oxygen is my balance gas. And then NOx is created when I put air under extreme pressure and temperature, over 2,500 degrees Fahrenheit, and I bond the oxygen and nitrogen into oxides of nitrogen. And that can be nitrous oxide or nitrous dioxide. Many times it's nitrous dioxide, but can be either one, and that's why it's displayed as NOx. So rich air fuel ratio, there is less than 14.71 pounds of air available for every pound of fuel. This can result in misfires and incomplete combustion, creating higher CO and HC levels. Normally, CO2 would be created by the combustion, but the lack of oxygen, there is not enough to completely oxidize the carbon, resulting in incomplete combustion and a misfire, allowing unburned hydrocarbons to reach the exhaust stream. With a lean air fuel mixture, there's more than 14.71 pounds of air available for every pound of fuel. This can result in misfires and excessive heat, causing higher HC and NOx levels. When the air volume is too great for the amount of fuel introduced in the combustion chamber, all of the oxygen will be used to oxidize the hydrocarbons. However, since the mixture is out of balance, there will still be some hydrocarbons without oxidation. This results in HC reaching the exhaust stream. So what happens is the oxygen actually in nitrogen becomes almost like an insulator around some of the hydrocarbon to where the flame front can't get there, and therefore it doesn't burn. And that's why even with a lean mixture, even though I have plenty of oxygen to oxidize all the hydrocarbon, because of poor flame propagation, I cannot get to all the hydrocarbons to oxidize them, and therefore I'll end up with unburned fuel. We call that a misfire or a lean misfire. When the air-fuel mixture is lean, the temperature of the burn is increased due to increased oxidation. The heat is contained for a short period of time in the combustion chamber. When the temperature exceeds 2,500 degrees Fahrenheit, the oxygen and nitrogen molecules from the air are bonded, creating oxides of nitrogen. So that 2,500 degree Fahrenheit has always kind of been a critical number. And that's why lean mixtures create NOx up until we get to about 16:1 air-fuel ratio. After about 16:1 air-fuel ratio, we start misfiring. When we're misfiring, we're not burning all the hydrocarbon, therefore resulting with the raw gas still in the combustion chamber of a cooler mixture, and NOx starts to drop. And we'll see that on the following slides. So here is a stoichiometric mixture. We can see the white in the middle is kind of my ideal area. And then as I go to the left, I go rich. As I go to the right, I go lean, which is my pink and my blue areas. So what we have is I have a vertical line that's going to cross each of these gases as we move between rich and lean. So right now I'm at a stoichiometric level. And at a stoichiometric level, I'm in balance. My CO2 is peaked. That's my efficiency gas. My NOx is going to be under 400 parts per million, so it's at a controllable level for my after treatment devices, such as my catalytic converter, or even my pre-treatment, such as an EGR valve. Hydrocarbons is at about their lowest level because I am most efficient. So if I'm more efficient, that means I'm oxidizing more of the hydrocarbon, means I'm going to have less left over. My CO is relatively low, under 0.5%, and my oxygen is also low, under 1%. So this is what we look at with a stoichiometric mixture. So the purpose is to show what happens to exhaust levels when the average air-fuel ratio goes richer or leaner than the preferred range. So the vertical line represents a specific air-fuel ratio, 14.7:1. And each dot indicates that the air-fuel ratio here on the line represents, in this case, the stoichiometric ratio. So just to reiterate what I already said, CO2 is at its highest point, 50%, and NOx is normally below its normal range of 400 parts per million. Hydrocarbons are below 50 parts per million, oxygen is less than 1%, and carbon monoxide less than 0.5. So this is where I'd like to be. So now let's see what happens if I go slightly rich. So as I go slightly rich, air-fuel ratio is now 14.3:1. So if I take this now, I can see I'm down to 14% CO2, 350 parts per million. NOx has dropped because it's a richer mixture. Hydrocarbons has gone up 90 parts per million. CO has gone way up because CO is a lack of oxygen, so it's gone up to 2%. And O2 is down to under 0.4%. Now let's go even further richer. So now I'm really rich. Now CO2 is going to be under 12.5%. NOx is not a problem because I have a very rich mixture. Yes, you have a question.
Yeah, I have a question. Is this a ratio for gasoline or diesel?
Gasoline. Everything we're talking about is gasoline.
Oh, okay. We're not in diesel yet. Okay, thank you.
Nope. So the change in gas rate is the air-fuel ratio, enriches even more to 13.5. And oops, thought I was going to get numbers. And so hydrocarbons is up to 140 parts per million, maybe even higher. CO is at 5%, and O2 is less than 0.1%. So you can see how my gases have all shifted as I went rich. Now, if I come back to stoichiometric, and then I can go slightly lean. So as I go slightly lean, I'm now at 15:1 air fuel ratio. And I can see that my CO2 again is dropped because CO2 is at its highest point at 1 lambda. NOx has gone up to 720 parts per million. Hydrocarbons have gone up. O2 has gone up, and CO has gone down. If I go even leaner yet, I'm down to 13% CO2, over 1,100 parts per million of NOx, over 60 parts per million of hydrocarbons, 3.5% O2, and no CO. So you can see based on my mixture, it affects all of my gases. So mixture is critical. If I don't have good mixture control, then I can't control the gases correctly, which means my other devices on the car that are designed to help control emissions, such as a catalytic converter, such as an EGR valve, such as air injection, such as any of my other emission control devices, are not going to work correctly unless I'm at the right mixture. Because if I'm at the right mixture, I'm making more of these pollutants than what these systems are capable of controlling. I basically exceed the range of what they're able to get rid of or what they're able to control. Or even if they're able to control something like hydrocarbons for a short period of time, like we see here with a lean mixture, it's going to greatly reduce the life of my catalytic converter. And that's why some people have had experiences where they got to put a catalytic converter on their car today to get it through smog, but 2 years from now it needs a catalytic converter again. And they're like, well, these aftermarket converters really aren't any good. No, your car is killing the catalytic converter. It has nothing to do with the catalytic converter not being any good.
Question for the temperature.
For the what?
Question I have, the 25 degree Fahrenheit is the maximum it can go, but iron melt down less than 2500 Fahrenheit. Iron. So how the sparking chamber exist?
How does the sparking chamber exist?
Yeah, because temperature is too high, so all the metal go melt down.
No, it doesn't melt down because the 2500 is at the flame kernel. It's not throughout the combustion chamber. So the valves are not 2500 degrees, but combustion chamber temperatures are hitting 2500 degrees. And it only does that for a very, very short period of time.
Okay, very
so
short.
it's not a sustained temperature, which you're right, would cause things to melt down. It's only happening for a split second.
Like a momentarily, this spark happen?
Yeah, the 2500 degrees is happening literally in milliseconds.
Oh, millisecond, okay.
So we can take the 2500 degrees a couple milliseconds here and there. We just can't do it. You're right. If it was 2500 degrees all the time, we'd melt the engine down. You're absolutely right.
Okay.
Good point.
Thank you.
Okay, so which emission will not go up when the mixture is too lean?
Oh, crap.
I just showed you guys lots of pictures.
Yeah,
Yeah, I know.
but carbon dioxide
Let's
not
go-
going up.
Let's go back to the picture.
You're right. Carbon dioxide will not go up because carbon dioxide is my efficiency gas. So it is at its highest at 1 lambda. So if I go slightly rich or slightly lean or very rich or very lean from 1 lambda, CO2 has to drop.
Yeah.
When I go lean, my NOx, my O2, and my HC will all go up. But the key here is, and really the whole purpose of the question, and you got it right, is I want you to understand that CO2 is at its highest at 1 lambda. So if I go rich or I go lean, CO2 has to go down. So that would be the only gas here that can't ever go up when I go lean, because it's at its peak when I'm most efficient.
So that's number
I
one.
can back up to a picture here. So here we go. We see CO2 at the top. It peaks at 1 lambda. As I go lean, it dropped. My NOx, my hydrocarbons, and my oxygen all go up when I go lean. So we got lean. Kind of, sort of. Well, let's try rich. What emission goes up with a rich mixture?
O2.
O2,
No.
CO2,
O2 can't go up because O2 is free oxygen. If I have a
Number
rich
one.
mixture, I have a lack of oxygen, so oxygen can't go up. It'll only go up if it's lean. You're right. Number 3, carbon monoxide. Because carbon monoxide is a lack of oxygen when my mixture is rich. It's because I have a lack of oxygen. So CO is the only gas that would go up. NOx is a result of excessive heat. We get excessive heat in a lean mixture. A rich mixture runs cooler. And CO2, as I discussed before, is my efficiency gas. So it'll always be at its peak at 1 lambda. What emission is at its highest when the mixture is stoichiometric?
HC.
No, HC isn't going to be, HC is lowest when we're stoichiometric.
O2?
What's that?
O2?
No, O2 would be at its highest when we're very lean.
CO2.
CO2, it's my efficiency gas. It is at its highest point. It's at its peak when I'm stoichiometric. It goes down whether I go rich or whether I go lean.
Gee.
So it gets a little confusing, doesn't it?
Yes.
Okay, so I'm going to give you guys a couple tricks to help you remember. One is our gas terms. In other words, what we call gases. And I've used these words, and here I put it in a slide. And this is because when I learned these, they didn't use clear words, and it made it very confusing. And it made it very confusing learning other systems. So hydrocarbons, what's a good way of describing hydrocarbons?
Gas.
Unburned fuel, okay?
Unburned. Yeah.
Carbon monoxide, what's a good way of describing carbon monoxide?
Poison.
Burned fuel.
Well, it is partially burned because it's partially oxidized, but that gets kind of confusing because what's the difference between partially burned and unburned, and we're kind of splitting hairs. So then I think a bad spark plug could cause CO because I partially burned it, and a bad spark plug can't cause CO. So why did I partially burn the fuel? What am I missing?
Oxygen.
Oxygen.
Oxygen, right. So carbon monoxide is really just a lack of oxygen. Oxides of nitrogen. What's a good way of describing it?
no clue.
Okay. Well, let's look at some of the things that can cause NOx. If I run lean, it'll cause NOx because the engine runs hotter. If I advance my timing, it'll cause NOx because my engine will run warmer. If my car's overheating, I'll make NOx because it's running warmer. Because NOx is made by what? Excessive temperatures under pressure. So could I call NOx excessive heat? Does that work?
Yeah.
Which means anything that makes excessive heat can make NOx. You see how this kind of starts to, by having good terms, now I can start looking at what's going on and come up with some ideas on what might cause things. So a carbon dioxide, what's a good way of thinking of carbon dioxide?
Oxygen burn.
Well, oxygen is burned. And if I'm burning oxygen really well and burning my fuel really well, am I being efficient?
Yeah.
So could I call it my efficiency gas since it's at its peak at 1 lambda when I'm most efficient?
Yeah.
Okay, and then I have oxygen. And if I have too much oxygen, I'm lean. If I have too little oxygen, I'm rich. So oxygen is what? It's a balanced gas. One way I go to rich, one way I go to lean. So these are good gas terms. These are terms you'll probably see again. This is something you guys need to learn. You guys should also understand the relationship of emissions to mixture. And this chart is a great way of learning this. This is about engine output emissions. And we see our CO2, our NOx, my CO, my O2, and my HC. And what I've always done when I've taught emissions is I have had my students learn this chart. Learn what the different things on this chart are without names. Because when you go to take a test, you can only bring in what's in your brain. And it's really easy to get turned around on emissions. So by remembering this chart and remembering the terms, if you know those two things, there's no emission question as far as what goes up when or whatever that you're going to get confused by. And I've taught this for a number of years, and it's always funny because I'd go after I give a test and I'd look and I'd see this chart drawn on tests, drawn on desks, all kinds of stuff. Matter of fact, as soon as I say go on a test, first thing they do is draw the chart so they don't forget it. This is a great chart for a reference. And if emissions is something you're interested in or something pursuing, I highly recommend learning this chart. Obviously, since we're online, the test is at home, so you're a little more open book. If it was in the classroom, it would not be open book. I'd be telling you all to learn this chart because this is important. So what emission can be described as excessive heat?
Oxide nitrogen.
Yep, number 3, oxides of nitrogen. And so then we talk a little bit about using a scale to measure our air-fuel ratio, and that's lambda. And we already went through lambda. So I'm going to jump ahead in the presentation here a little bit. And I'm going to do a little bit of lambda refresher with you guys. So if there is an exhaust leak with a lambda calculation, will be artificially what?
Lean.
Lean, absolutely. Because we're measuring oxygen available to oxygen required. So if I have an exhaust leak pulling air in from the outside, as I showed you it would do in the video, then my calculation is going to indicate lean, which isn't necessarily how the engine's running, but it's the gases I'm measuring.
Of the highway. Yeah.
So which of the following is a rich lambda value?
102?
1.02. Number.
No, 0.98. Remember, it's the ratio of oxygen available to oxygen required. So if I have less oxygen available than I require, my ratio will be less than 1. If I'm running lean and I have more oxygen available than I require, my ratio will be over 1.
My mic wouldn't unmute. It's 3.
Yep, you're right. High NOx can be caused by which lambda value?
Number 3.
No, number 3 would be a rich mixture, which would mean I'd be running cool, so I wouldn't make NOx.
Yeah, 2.
Has to be 2. It's the only one of those answers that's what? A lean mixture. And it's very excessively lean. It's outside of my fuel control range. So it would be number 2.
So NOx mean heat. Is
NOx means heat, and a lean mixture runs hotter. So like anyone who has worked with little, 2-stroke engines or motorcycles or things like that, know that a lean mixture, you'll melt the piston down. Well, the reason for that is because excessive heat.
About the smoke check. The smoke check, the NOx show the normal engine. NOx.
Yeah, we normally will see some NOx. Obviously, I mean, if an engine's running good and the catalytic converter's good and all the emission controls are good, I have seen cars that put out 0 out the tailpipe when we measure it. But it's not uncommon to see some NOx, and we measure it in parts per million. And so it's not uncommon to see a couple hundred parts per million of NOx coming out the tailpipe. Some older vehicles have standards of a couple thousand parts per million, where a new vehicle might put out 1 part per million. So you can see where new cars are really a lot cleaner than old cars.
Right.
Where when it comes to emissions, because now we measure it, if I go soup up my car and it's putting out 3,000 parts per million of NOx or hydrocarbons, which we also measure in parts per million, and a car that year, make and model, when it's running right, puts out 1. That means what? I'm polluting as much as 2,000 cars when I drive my car?
Yes.
That's kind of selfish of me, isn't it?
Selfish and
I mean,
Very
so
old
people tend to think of their car as, I'm not hurting anybody. If no one's concerned but mine what I do with my car. It shouldn't matter if my car pollutes. Why is the state doing it? It doesn't hurt anybody. Those are all fallacies. The bottom line is it hurts everyone because we all got to breathe the same air. And when we modify cars or when cars are not running correctly, they pollute sometimes hundreds of times what they would if they were running correctly. I mean, if you ever watch a TV show from the late 60s, early 70s, we were watching a show this weekend with my wife, and boy, they start the car and a big bunch of smoke comes out the back and smog, and then they take off and it puts out smoke out the tailpipe. That was normal. That's how those cars ran.
Yes.
We don't see that anymore, do we?
No,
We
it's
start a
true.
car or drive a car?
In Mexico, we can see anything.
Yeah, well, that's Mexico. They don't have the same rules that we have here.
Right.
That's also why their air in Mexico City is so bad. So high CO emissions can be caused by which lambda value?
High. 1.05.
0.94.
Has to be 0.94 because CO is a lack of oxygen.
3.
If I have a lack of oxygen, my ratio of oxygen available to oxygen required has to be less than 1. Therefore, the only possible answer would be number 3. And you're absolutely right, Jose.
I'm gonna comment something. So what are we getting over here is the result that is coming out now, how I have to run.
Well, right. This is what happens if the car was running at possibly a 0.49 lambda. This is what emission would go up. So it will go up at that, just like NOx will go up at 105, 1.05 lambda or 1.04 lambda. NOx would go up. Can the car handle that? It depends on the car. So Some cars, if they're a 0.94 lambda, they're going to fail a smog inspection. Other cars at 0.94 lambda, like BMW, that actually will run in that range, run there for a reason, and they have other emission controls to help control the CO. But what they don't want is the NOx. So they run rich to try to prevent NOx, and then they have to use a really big cat to control the HC and CO. So there's different emission strategies that the manufacturers use to combat this. But the the whole purpose is to try to understand, as we move rich or lean, what emissions are going to be affected during the combustion process. So, for example, I've had a Toyota that fails for high CO at 0.94 lambda. When I adjust fuel control and fix the fuel control issue, so I'm at 9.8 lambda, the car passes. Because the after treatment device, the catalytic converter, everything else in the car is designed to run at 0.98 lambda. 0.94 is too rich and it can't control the extra CO. So also the other thing that happens is, as I go rich, my converter loses its ability to convert CO and HC. And as I go lean, the converter loses its ability to convert NOx. So at the same time my engine is making more of these gases, my catalytic converter becomes less efficient at getting rid of them. So it's kind of a double whammy. So, cars are very, very lambda dependent, very, very sensitive to how they work as far as running clean and passing an emissions test.
But carbon monoxide 14.7 is a maximum or minimum at that time?
Is
What do you mean maximum or minimum?
The lambda is 1, which is a normal operating range.
Right.
And that time air is 14.7. So what the carbon monoxide existing is the lowest.
Yeah, well, it's not going to be the lowest. It'll get a little bit lower as we go lean, but it is manageable.
Right.
Okay. So, again, these are engine output emissions. So what I want from my engine output is not necessarily perfect clean emissions, because as I go too rich or go too lean, I can lower either NOx or lower HC and CO, specifically CO. But what I need is I need the right mixture in the correct range so my catalytic converter will be efficient. Because it's all about having the cat clean up what's left.
Okay.
What we don't want is the cat to try to clean up too much or clean it up at the wrong mixture, because then it won't work. And unfortunately, a lot of people replace catalytic converters trying to get a car to pass smog when there's nothing wrong with the cat. I can't tell you how many times I've seen customers make their problems worse by taking a factory cat off and putting an aftermarket one on, trying to get their car to pass smog. And all they've done is create more problems, because there's nothing wrong with the original cat. So it's truly all about fuel control first. And until fuel control is working correctly, nothing else is going to operate efficiently. So I do this because, again, we're used to thinking rich and lean. I want you guys thinking about lambda and how lambda affects emissions.
So Mr. Bryan, by getting rid of carburetors, more likely everything's going to run a lot better.
Oh, absolutely, because carburetors are very, very hard to control the mixture, for one. B, they're not efficient, which means my CO2 level is never as high on a carbureted vehicle, or almost never as high on a carbureted vehicle, as it is on a fuel-injected vehicle, because they're just not that efficient. So my emission standards are normally higher on carbureted cars than they are on fuel-injected cars. There are some exceptions, like my pickup truck, for example. It's carbureted, but it has to meet the same emission standards as the fuel-injected model that year. My truck doesn't have a catalytic converter, but yet the fuel injector model that year did have a catalytic converter. My truck doesn't have a computer to control ignition timing and fuel mixture, and the truck with the catalytic converter does, but we have to meet the same tailpipe emissions when I go get checked for smog. You don't suppose they want me to get rid of my truck, do you?
Nah.
So, matter of fact, I got to get it smogged by the end of the month. So that's coming up. Gonna have to drive it down and smog it.
That was one of the reasons I wanted to move to change the carburetor to the throttle,
Uh-huh.
be more efficient in gas and less contamination.
Yeah. Yeah, hopefully my truck will pass first time. It did 2 years ago when I smogged it. So hopefully.
I don't want to tell you, but I'm going to tell you. I'm from Calexico. I'm from that area, so
Right.
some of my vehicles have still my address out there, and it's not that I want to avoid it. It's just because I always try to keep my cars running to the best. But once you leave over there and you get your first test, you don't have to do it again ever.
Right. No, I know. It's a change of ownership area. And like your 91 pickup truck, that's a gray mark, or 90, what was it, your pickup? The 90,
Yeah, 91.
91. That's a gray market truck. Means it's from Mexico. So it needs to have a bar referee label on it and everything else in order to be smogged.
Yeah.
And that may or may not have been done. So I figured it was registered as a change of ownership or something else, and it fell through the cracks out there. But I'm here as an educator. I'm not the smog police.
Yes.
When you come into my shop and I'm smogging your car, then I'm the smog police. Here, I'm just an educator telling you guys how things work.
Yeah, I've just a lot of people doesn't know that, but the Imperial Valley is so contaminated that it doesn't make. That's what they say. It doesn't make any difference. But nevertheless, I always try to keep my vehicles to the best.
Yeah, no, it does make a difference out there. The issue we have with smog is under federal law, you can only put a biannual smog program in areas that either do not meet clean air standards, called non-attainment areas, or areas directly next to non-attainment areas. And since Calexico is out there so far, even though it has issues, the valley out there is so big that they don't get the inversion layer during the summer because there's a pretty good breeze out there most of the time. And so therefore, when they test for smog, it doesn't violate the federal levels, even though there's plenty of pollution.
Oh,
And you
okay.
compare that to the Central Valley, which does get an inversion layer in the summer and does get horrible air pollution because that valley is so big, it just becomes one pocket and the wind doesn't blow it over the mountains, where the Imperial Valley doesn't have that issue.
No, but
Okay.
global.
I thought it was because of the contamination, because they do have a lot of contamination out there. It's I don't want to say it the way, but it's because all the factories that cannot work in the United States, they take them to Mexicali and now
Right.
that border the lines and they contaminate to the
Oh,
without.
no, I know. And that's an issue. But I'm just explaining why we don't have a biannual smog program out there, is that legally we can't.
No, but when we talk about the emission and air pollution, is any connection with the air pollution to the pandemic?
No.
Okay.
Matter of fact, air pollution has gone down during the pandemic because people are driving less
Right.
and factories are closed more.
But pandemic, coronavirus increasing and COVID-19 more.
Yep. No one wants the Rona.
Yeah.
So let's look at some oxygen detecting sensors. So we have a couple of different kinds of oxygen detecting sensors. We have a zirconium sensor, which is the most common sensor. It's still used today. A titanium sensor, or titanium, and it was only used on some specific Nissan and Toyotas and on Jeeps, and we haven't used it since probably late 80s, early 90s. So it's in the Wayback Machine. And air-fuel ratio sensors, which we started using in the 90s and continue to use today. So the two sensors you're going to see on a car today are an air-fuel ratio in front of the catalytic converter. We never put an air-fuel ratio behind the catalytic converter. There's no reason to. And behind the catalytic converter, we use a zirconium sensor today. I don't think anyone is still using a zirconium sensor in front of the catalytic converter, although we did for a number of years up to at least 2010. So that's kind of a history of what you'd expect to find. They're located in the exhaust stream and provide feedback information to the PCM about the relative oxygen content in the exhaust. So this is really more about relative than absolute. In front of my catalytic converter, I have more oxygen than I do after my catalytic converter. But yet my oxygen sensor in front of the catalytic converter may say it's rich and my one after may say it's lean, because they're not looking at just oxygen percentage. They're looking at the oxygen ratio compared to the other gases. So here's a cutaway of a zirconium oxygen sensor. Not that we're ever going to be cutting one open. But what it has a screen around the edge of it. I don't want timing. It has a screen around the edge of it. There's a ceramic coating in there. And there's a wafer in the top, which consists of some platinum electrodes and a zirconium electrode that create electricity. So this generates its own electricity based on relative oxygen content. And the computer looks at that electrical signal and makes a decision on how it wants to operate the vehicle. Oh, come on. So here we can see the center electrode made up of a ceramic material called zirconium. Two platinum electrodes make up the inner and outer surfaces of the center electrode. Must be kept above 600 degrees in order to work. Now, all zirconium sensors work the same way electrically. The biggest difference we have in them is how they sample the gas. So down here at the bottom, which is the thimble part, this one you can kind of see has some slits there. So some of them have slots, some of them have round holes, some of them different things. That affects how the gas gets into the sensor, which affects the sensor's reaction time. And when we replace these sensors, we always want to replace them with the brand that it left the factory with. So there's only 3 companies that make these sensors. There is Bosch, there is NTK, and there is Denso. So if you're buying a sensor made by someone else, they're either reboxing one of those sensors or they have a sensor manufacturing plant and they're buying them out of China or whatever. Odds are 50% your car won't work right after you put it on. You always want to use the factory sensor. Now, that doesn't mean I need to necessarily go to Ford or I necessarily need to go to Toyota. I may, but what it does mean is I need to match up the brand on the sensor to the brand that came from the factory. And don't assume that just because it's an Asian vehicle, it's going to use like an NTK sensor or a Denso sensor. Because Denso is Asian, or Japanese company. Well, if I'm working on a Toyota, most of them use a Denso, a couple of them use an NTK. But if I'm working on a Nissan, for over 20 years, Nissan used Bosch sensors. If I look at a BMW used to use Bosch sensors, and then they've gone to using NTK sensors. Chrysler uses NTK sensors. So and I can buy NTK, Bosch, or Denso aftermarket. So a lot of it's taking the time and either, if it's the original sensor, clean up the sensor and see who made the stupid thing. Sometimes it's get a picture of the factory one and then look on the side of it and see who made it for Toyota, Nissan, Honda, whoever. And sometimes you're locked into getting a factory one. And there's a couple applications I will get dealer sensors for. And sometimes getting a dealer sensor can actually be cheaper than getting an aftermarket sensor, and they actually fit right. But it is critical. I fixed a lot of cars simply by taking the O2 sensors out that a customer put in and putting the correct sensors in. And I've gotten paid diagnostic time to figure out that was the problem, as well as paid to change the part and everything else, because the part they put in was not correct for the vehicle. Even though at XYZ Auto Parts, the sales guy at the counter looked it up in the catalog and said that's the one that fits. Fitting and being correct are two different things, and for oxygen sensors, that's critical. So oxygen sensors started out as a single wire sensor. So my single wire zirconium sensor was grounded through the threads. Doggone it. I gotta get the timing out of this. Was grounded through the threads, and then a single wire sent an electrical signal to the computer. And it had to be open in here to the outside atmosphere, because what we're going to do is the voltage is generated by electrons going from inside to outside or outside to inside, but electrons passing through the zirconium and platinum plate. And so if the outside of it got plugged up with dirt, the sensor couldn't work. So someone who went off-roading or went through the mud, they might have a car that ran really bad afterwards because the sensor couldn't breathe. We also had 2-wire sensors, which basically, instead of grounding through the threads, now had 2 wires, one going to the ground, one for the signal. We had 3-wire sensors in the case of Ford, where we used put a heater on it, since these need to work at 2,500, I mean, at 600 degrees. One of the issues we have is when it's mounted here on the exhaust manifold, it gets to 600 pretty quick. A lot of the early ones were actually mounted all the way down in the exhaust pipe. And so it would take them a long time to get hot. And even when they got hot, if you came to a stop sign, they might cool off and stop working. So we started putting heaters on them. So here's a 4-wire sensor that has a heater. So I have a ground and a signal return for my sensor, and I have a ground and power for my heater. And this is ticking me off. And so we turned the heater on to get it up to 600 degrees, and then we traditionally just turn the heater off once it got hot. So we still had some issues with coming to a stop. It might cool down and so on. Later models keep the heater on all the time. So again, this is a 4-wire sensor. So they do sell some universal sensors where you're supposed to, here's your 4 wires, you cut it and you splice it into the factory connector. Never use those. That's not the right one for your car. So when we look at O2 sensor operation here, my oxygen outside has about 21% oxygen. If I'm above 1 lambda lean, I have very little electron flow through my wafer. As I become richer and my lambda goes below 1, then I have greater electron flow, which increases the voltage. So it's the electron flow through the platinum and zirconium wafer that generates the voltage. And so this is about relative lambda, and it's comparing itself to the outside oxygen, and it needs that outside oxygen in order for the catalytic process to happen inside the oxygen sensor. And One reason why this is relying on lambda, not just oxygen, is I can't catalyze oxygen. I need to catalyze something else. And then I can look at the relative content of the oxygen, and that's going to affect how it catalyzes the other materials. And different chemicals have different lambda or balance numbers. So CO2 is perfectly balanced. CO2 is 1 lambda. So my zirconium oxygen sensor generates between 0 and 1 volt, depending on the relative O2 exhaust content. 450 millivolts is normally used as a switch point. Above 450 millivolts, the exhaust is considered rich, and below 450 millivolts is considered lean. The sensor switches very fast. It must switch under 100 milliseconds when propane is added, and it operates at 600 degrees Fahrenheit. So here is my lambda sensor. So this is our zirconium oxygen sensor. So here is 1 lambda. This line represents 1.025 lambda. This line represents 0.975 lambda. Now what we can see here is my oxygen sensor voltage goes between low when I'm lean to high when I'm rich very quickly at 1 lambda. So a very, very narrow range. So what this tells the computer is binary, rich, lean, rich, lean, rich, lean. It can't tell it how rich or how lean. All it says is rich, lean, rich, lean. Well, a computer is a clock. So if I am rich half the time and I'm lean half the time, I should be pretty close to the right mixture of 1 lambda. And that is the philosophy that uses. So it takes this sensor signal, goes into the computer, and the computer, which is all 1s and 0s, converts it to rich, lean, and then says, hey, I need you to spend this much time rich and this much time lean, and that's going to give me the mixture I want. So if I look at my oxygen sensor here on this slide, we can see it's cycling from under 175 millivolts up to, we want to go over 800 millivolts. So we're hitting right around 800 millivolts here. So it's cycling. So I'm looking at 5 seconds of time. Here's my 0 volts. Here's my 1 volt. And we can see this cycling as the car goes rich, lean, rich, lean. Now the sensor is cycling, but it's cycling because the computer is making it cycle. In other words, when the voltage is high, the computer takes away fuel to make the voltage low. When the voltage is low, the computer adds fuel to make the voltage high. When it's high, the computer takes away fuel to make it low, and then again and again and again. So the timing component in this computer is to go from rich to lean, rich to lean, rich to lean. We're not going to sit there and stay at one spot. And the reason for that is I have to go rich, lean, back and forth, or my catalytic converter will not work. So we do this for the sole purpose, it's the technology we had to control fuel control at the time, but the sole purpose behind doing this was to control the catalytic converter and make the catalytic converter efficient. So this is all about driving the cat. Yes.
I was looking at one of the classes over the weekend, and some vehicles will send rich in the beginning when you start your vehicle, so get the cat working at the right temperature.
Correct. And we talked about that last week. You're absolutely correct. So what we want to do is the cat to light off. And we normally do that through post-injection. So they're calling that a stratified charge, which technically it's not, but okay. But they're doing that through post-injection because what I need in order to get the catalytic converter to light off, I have to have air and fuel. So what they do is they run a lean mixture in the combustion chamber, so there's leftover oxygen, and then add fuel as the air fuel mixture gets ready to leave the combustion chamber, usually towards the end of the compression of the power stroke. And that way you're pushing this really, really hot oxygen into the exhaust manifold with this unburned fuel, causing it to burn in the exhaust manifold, which is what lights off the catalytic converter. So they're not running the mixture in the combustion chamber rich, per se. They're actually running a lean mixture with post-injection. Because if I ran a rich mixture, there'd be no oxygen left over, and all the fuel in the world isn't going to light off the catalytic converter if there's no oxygen to oxidize the fuel. So it's a little more complicated than that, but you have the right idea that we're using extra fuel to actually burn in the exhaust to heat up the catalytic converter.
All right.
And if I look at the total mixture used, yes, we are using more fuel than we do for a stoichiometric mixture, but we're not putting it in all at once. So sometimes the books overly simplify things a little bit. But nope, that's exactly what we're doing. So we do that. Some manufacturers use air injection, and they'll run the mixture rich, and then they'll pump in additional air into the exhaust to ignite the leftover fuel. So we do that on cars that aren't direct injected. And we did that on a lot of European vehicles. So they were running a rich mixture, then they'd inject air. But I have to have some way of getting that extra air in there with that extra fuel. So when a zirconium O2 sensor voltage is 600 millivolts, what is the air fuel mixture? Well, what did we come up with?
Number 3, stoichiometric.
It is not stoichiometric. Stoichiometric would be 450 millivolts. That's my switch point.
Rich.
So if I'm above 450, I'm one thing, and if I'm below 450, I'm another. So if I have
Is
a rich
stoichiometric?
mix, what's that?
It's lean, but stoichiometric is 450.
Stoichiometric is 450 millivolts, basically. We use that as a switch point. If I have over 450 millivolts, I would be rich. If I'm under 450 millivolts, I would be lean. So if I back up a second to our slide, we can see here, if I'm above 1 lambda, which is lean, I'm normally going to be under 300 millivolts. If I'm below 1 lambda, which is rich, I'll normally be over 600 millivolts.
Oh, so it's rich.
Yep.
The answer.
Yep, the answer is rich.
Oh, I changed it.
Or under 1 lambda, which is rich. So it gets kind of confusing because we have a lot of different pieces of the puzzle. We have an air fuel ratio, we have lambda. Now we've just thrown in O2 sensor voltage. So so a lot of different scales we use for rich and lean. So you're right. The answer here is rich. And I can read this. You saw me read it with a scope. I can read this with a DVOM. Matter of fact, that's what we used to do before we had scopes. It's not, I can tell if it's dead. I can tell if the car's stuck running rich or stuck running lean. So I can still get some good information. Because it should be going what? Up and down constantly. I should be going rich lean. So my DVOM should be going 700 millivolts, 100 millivolts. 600 millivolts, 300 millivolts. Well, we should see that it constantly changing. If I hooked up my DVOM and it just sat at 800 millivolts all the time, maybe, man, this car is running rich. If it was stuck at 100 millivolts, we'd be saying, man, this car is lean. If it was stuck at 0, we'd say the sensor's dead. Or it's really, really lean. So I can still get some information using a DVOM and connecting it to the wire that comes from the O2 sensor. But a scope is the preferred way of doing it. So that's zirconium sensors, and we use them after the Cali converter. We used them before and after the Cali converter for a number of years, but they're still in use today. So we still need to test them. We still need to understand them. Titania sensors are a little bit different in that they do not generate a voltage. They have to have voltage applied to them, and the titania changes resistance based on relative oxygen content. So depending on how they're wired, either you could get low voltage with a lean mixture or high voltage with a lean mixture. Depends on whose car you're working on. So some Toyotas and Nissans used a 0 to 1 volt sensor, and it would act very similar to a zirconium sensor. So a lot of people would replace it and not even know. As long as you ordered the sensor for the application, put it in, your scope pattern looks about the same, you're really no wiser. And so a lot of people didn't really realize. What got interesting was on the 87 to 90 Jeep 4-liter Cherokees, because they did two things. First of all, they used a 5-volt reference instead of a 1-volt reference. And the other thing they did is they made it opposite. So a lean mixture gave you a high voltage and a rich mixture gave you a low voltage. Now, fortunately, there's not that many 87 to 90 Jeep Cherokees out there anymore. So you may or may not ever see one of these. But if you see 5 volts on an O2 sensor circuit, it means you're working on a titania sensor on one of these Jeeps. And there are still some of these out there. But the key point is the high oxygen content equals high sensor resistance. So it depends on where the sensor is located in the circuit. Because if we look at our electrical circuit here, this is identical to an engine coolant temperature sensor circuit. High resistance would give me high voltage at the sensor. Low resistance would give me low voltage at the sensor. Doesn't this look exactly like our ECT or IAT schematic we looked at several weeks ago? Series circuit, 2 resistors, 1 fixed, 1 variable, 5 volts applied, and we monitor the signal voltage between the 2 resistors. So electrically, this works exactly the same way as our ECT and IAT sensors did that we talked about when we covered sensors. And that's why I think it's so powerful. Once we understand how electricity works, understand how a circuit works, once we learn one thing, all we need to do is learn to recognize it in other things. And wow, I know how that works now. This one, again, same thing, except for in this case, my voltage is here. So I have no resistance between my voltage and my variable resistor, my fixed resistor and ground. That's why high resistance equals 0 volts, where low resistance here, low resistance here would give me 0 volts. High resistance would give me 1 volt. So that's and it just comes down to how the circuit's wired. Like I said, there aren't many of these out there. You're talking 80s, it's Toyotas and Nissans. It's 0 to 1 volt. If you're testing an O2 sensor and it doesn't move or the voltage is fixed, you're probably going to replace the sensor. As long as you order the right part, it really doesn't matter whether it's titanium or zirconium, as long as you're putting the right one in and the part store gave you the right part. The Jeeps are the ones that get people's attention because they see 5 volts and they think something's shorted or it's a bad computer or something really weird going on.
Mr. Brian,
Yeah.
on one of the tests, it asking what voltage would it have, and to me, what I was reading, it's supposed to be 1 volt, but the right answer was up to 5 volts.
What, for an O2 sensor?
Yes, for O2 sensor.
Yeah, and really, they should have specified what kind of O2 sensor. Because, yeah, for any kind of O2 sensor, it could go to 5 volts because of these 3 years of these titania sensors. If I specified a zirconia sensor, it would be 0 to 1 volt. So the book really should have specified the type of sensor in the question and not just left it as a vague, well, if you're on Mars and you're eating a Kit Kat bar, How long would it take you to swallow? I mean, is that kind of thing so vague? And that's why a lot of times I don't use the book questions in my tests. I use my questions because of that vagueness. But they are technically correct. If I just asked you about O2 sensors, 0 to 5 volts would be a range because we didn't specify what kind of O2 sensor. So we can see the different points on each of these, my VREF, my signal return on my ground. And again, on this one, lean mixture is high voltage, or here lean mixture is low voltage. It's because the variable resistor is on the ground part of the circuit for 1 and the voltage supply part of the circuit for 2. So that's all I got for titanium sensors. You guys may never see one, but I would have been remiss not to mention them. So let's get into some current technology and look at air-fuel ratio sensors. So the following is an explanation of how a wideband or broad plein air or air-fuel ratio sensor operates. So there's only 2 companies that really make these. One is Bosch, the other is Denso. So everything in the world has either a Bosch or a Denso pretty much when it comes to AF sensors. So it kind of makes it a little simpler. I'm sure NTK does sell some, but those are the 2 primary ones we see. So our simple O2 sensor that we already looked at, our zirconium sensor, is constructed with 2 platinum electrodes and a zirconium dioxide element between the electrodes. So there is our little thing. And so when I have exhaust in the exhaust pipe and fresh air outside, the platinum electrodes react, a Callick reaction, to the potential difference in oxygen content between the outside air and inside the exhaust pipe. And this potential difference creates an electrical current or voltage. And we're going to see a little pass through here. Oops. Animation here. So I have an O2 ion, and it's going to go through. The richer the mixture, more ions that flow, the more voltage is generated. So this is our conventional zirconium O2 sensor. So current is developed because the platinum plate and the exhaust steam will dry oxygen ions from the fresh air side to the exhaust as part of a Callick reaction. So in other words, what it's trying to do is rebalance lambda. So the more it's trying to rebalance lambda, the more ions that are flowing through. As the transfer O2 ions through the platinum plates, it creates current flow. The less O2 in the exhaust, the higher the current flow, the higher voltage is generated, due to the larger potential difference in ion concentration from the outside air to the inside air of the exhaust. The zirconium oxygen sensor just described worked well for time, but unfortunately, this type of sensor is prone to producing wide voltage fluctuations above and below the 450 millivolts and very limited range. And we saw that in the lambda picture that it really only switches at 1 lambda. The PCM was forced to make fuel and timing adjustment decisions based on an average of these fluctuating symbols. With the government regulation requirement for low and ultra low emission vehicles, more accurate method was developed on the exhaust content in a wider range, upwards of 23:1. So an air fuel ratio sensor will accurately measure the mixture from about 10:1 all the way up to 23:1. So a much wider range, which is why it has that wide range or air fuel ratio sensor name. So here we're looking at an air fuel ratio. This is just a generic picture I grabbed. Actually, it wasn't grabbed by me, but it was there. So a new sensor was developed called a wideband or broad plein air fuel ratio sensor based on the operation of the old O2 sensor just discussed. Sensor actually has 2 O2 sensors built into it, housed in one area within a common chamber between them. So if I'm working on a Denso sensor, it's actually going to have 4 wires If I'm working on the Bosch design, it normally has 6 wires. And that's because the Denso does some stuff inside where it shares circuits, where the Bosch wires everything separately back to the PCM. There's one we're going to look at is more like a Bosch style, but you get the idea of what's happening. So the wideband plein air air-fuel ratio adds 2 chambers to the original zirconium sensor. We're going to add a diffusion chamber. And then we're going to add an air reference chamber, which is open to atmosphere. So what we've done is we've taken the outside air, and I've now given this sealed chamber, this diffusion chamber, that we're going to measure the difference between what's in the diffusion chamber and what's in the exhaust. So that relative difference is what generates the voltage. So we're still generating voltage the same way, but we're not using that voltage to control how the car runs. So between the diffusion chamber and the air reference chamber, we're going to put a second oxygen sensor. So this second oxygen sensor, again, has 2 platinum electrodes and 1 zirconium element. So these plates are wired in a parallel circuit with the plates to the left of the exhaust stream. So what's interesting about the zirconium sensors is that if they see that difference, they're able to generate voltage. However, if I apply voltage to it, it's able to move electrons through the plates, through the platinum and zirconium. If I change the polarity, it moves the electrons in the opposite way. So now we can use it as an ion pump. So instead of just reacting like we did when we sensed, I can now use voltage and switch the direction of current to use it as a pump. So now I can control the mixture or the amount of oxygen in the diffusion chamber. So this circuit has 2 sensors. They share a common ground, and we call it a floating ground because it's going to change polarity, basically. The sensor that is in contact with the exhaust stream is commonly referred to as the sense signal. And they're just going to call it sensor 1 for the sake of explaining how it works. The sensor in contact with the diffusion chamber and air reference chamber is commonly called the pump cell, which we're going to call sensor 2. So we have a sense cell, which actually senses what's in the exhaust, and a pump cell that we're going to use to pump oxygen ions in and out of the diffusion chamber. So on sensor operation, sensor 1 operates as a traditional zirconium oxygen sensor, sending high voltage signal above 450 millivolts to the PCM when the air-fuel ratio is rich, low oxygen, and low voltage signal below 450 millivolts when it's lean. The purpose of the diffusion chamber in sensor 2 is to counteract that change in the voltage of sensor 1 and keep it at 450 millivolts. So what we did previously is we looked at that O2 sensor and said, boy, you went rich, so now I want to make it lean, and you went lean, I want to make the car rich. Very binary. We're kind of chasing each other. And all I knew was rich, lean, rich, lean. Now what we're doing is I really want that sense to stay right at 450 millivolts. And what, as it tries to move, I'm going to exert pressure this way to hold it at 450. When it wants to go this way, I'm going to exert pressure this way to hold it at 450. That's my pump cell. So my pump cell is pumping to hold it this way or to hold it this way as it wants to move. And what we're going to do is we're going to measure the amount of effort required to keep it at 450 millivolts. That effort required is what allows me to see that much wider air-fuel ratio range of 10:1 up to 23:1, because now I'm just measuring how much force am I applying or how many oxygen ions am I flowing in order to keep that at 450 this way. And oh, we switched direction, I need to keep it this way. So instead of measuring how far it moves, I'm measuring the amount of effort it takes to hold it in one place. And that's why it's able to see such a wider range with a zirconium sensor, is this diffusion chamber and pump cell. So to keep sensor 1 at 450 requires that sensor 2 provide current flow, positive and negative, that will move O2 ions in the opposite direction that sensor 1 has them moving in relative to exhaust content. For example, if a rich mixture enters the exhaust system, low O2, many O2 ions will flow from the diffusion chamber through sensor 1 towards the exhaust stream, and sensor 1 voltage will rise. Got it. Now, when sensor 1 voltage rises above 450 millivolts, the PCM reacts by providing a negative current flow to sensor 2 to move the pump ions in the opposite direction back towards the diffusion chamber, thus limiting the O2 ion flow through sensor 1. So what we're doing here is we're holding that voltage right around that 450, and we're going to measure the amount of current, amperage, that we're having to flow through. In other words, how hard am I working in order to keep that first sensor at 450 millivolts? Pretty cool. So when the oxygen content in the exhaust system is lean, low ion transfer, the system reacts in the opposite manner. Sensor 1 sends a low voltage signal under 450 millivolts to the PCM. PCM sends a positive amperage signal to sensor 2 to pump more ions into the air reference chamber, through the diffusion chamber, to the exhaust stream, through sensor 1's plates. So this action causes more ions to flow through sensor 1 and brings the voltage up to 450 millivolts. So we don't care about the 450 anymore. I don't care about what the voltage there is at all. Matter of fact, I can't even read it. It's about the amperage. And for the most part, although I can read the amperage, where we used a lab scope to test zirconium sensors, and we still do, with air-fuel ratio sensors, we really rely on the scan tool, because it's an inferred value. They're also pretty good at setting codes when they don't work right. So as you can see, sensor 2 controls sensor 1's voltage by applying positive or negative current flow. The PCM monitors the current flow to make sensor 2, to make the change on sensor 2, and makes fuel and timing corrections based on the size of these changes. So now, what we've done on some cars is maybe I wanted to run it 16 to 1, 18 to 1, 20 to 1 when I'm on a real slight downhill over an extended period of time. So instead of cutting fuel off altogether, let's run it 20 to 1. We're not going to make NOx because there's no load on the engine. So it's allowed us to get better fuel economy, better control Also, if my car is running rich in the morning because it's cold, now I can actually decide how rich I want it to run, not just that it's rich. So I have a lot greater control. So if there is zero current flow on sensor 2, the air fuel ratio is its stoichiometric. I see my arrows off a little bit. And we're at 450 millivolts. So do you guys understand the difference between an air fuel ratio sensor and a zirconium oxygen sensor?
No.
Right
Yes,
side, the
no?
meter showing up, the arrow right side showing more than 40.45 volt. And
I just
up.
said my arrow is off. It fell out of my gauge. I need to fix it.
Okay, all right.
It's straight up and down. We get the idea.
Okay.
So sometimes when I move this stuff around, stuff doesn't always end up where I want it. But so a zirconium sensor can have 1, 2, 3, or 4 wires. An AF sensor can have 4 or 6 wires. Normally some of them have 5 because they blended, but it's a 6-wire connector. A zirconium sensor I test with a lab scope. An air fuel ratio sensor I normally don't. I mean, I know how to. I just never have because I've never needed to. I can't tell the difference between a 4-wire air fuel ratio sensor and a 4-wire O2 sensor, zirconium O2 sensor. It's impossible to tell the difference. So it really comes down to the importance of matching up part numbers, making sure things are looked up correctly. If I was to plug in a zirconium oxygen sensor into a vehicle that requires an air fuel ratio sensor or vice versa, I run a high likelihood of letting all the smoke out of the computer. So we always want to really make sure we identify parts correctly. Keep in mind, we don't use air fuel ratio sensors at all after the Cali converter. There's no reason to. Those are all going to be zirconium O2 sensors. And the way of thinking about oxygen sensors, whether it's a zirconium, a titania, or an air fuel ratio sensor, it's my computer's eyes. So it's the only way the computer has to see, did it get it right? Because all my other sensors are before the combustion chamber. My map, my mass, my RPM, all these other things that I'm looking at are before the combustion chamber. The O2 sensor is the one that says you got it right or you screwed up. So consequently, for the last, 30 years probably, 25 years, it is probably the most important sensor in the car, unless something else is out of range. Certainly for the last 20 years, it's the most important sensor in the car right after your cam and crank sensors. Because if the O2 sensor if the mass airflow sensor is guessing the wrong amount of air, it's the O2 sensor that tries to fix it. If the coolant temperature sensor is lying and we put the wrong amount of fuel in, the O2 sensor is the guy telling you to try to fix it. So it is real high priority. So it can cause a lot of weird issues with cars. I've had it cause cars to blow black smoke and die on the freeway. I've had it to cause cars to have one side of the engine stop running at idle and set misfire codes. I've seen a lot of weird problems with O2 sensors over the years. But it is the only way the computer has of seeing what kind of job it did after the combustion chamber. So these are extremely important sensors.
Last 25 years, you're saying that a lot of changes come, but why they don't copy from the aerodynamics emission system?
What do you mean the aerodynamics?
Means the aeroplane has also all these kind of some devices and research and development.
Oh, so that's not aerodynamics. You're talking aeronautics.
Aeronautic, yeah, sorry.
Okay. Aerodynamics is how much drag I have going down the road. Aeronautics. Okay, flying.
Aeronautic.
Right. Okay. So a couple of issues. Aeronautic engines tend to be turbine engines.
Okay.
So they run a very different fuel. Also, they're running a very different kind of fuel. Jet fuel is very different than gasoline. But their mixture is very altitude sensitive because obviously there's a lot less air at 40,000 feet than there is at sea level. So they do a lot of input controls for aeronautics. They don't do a lot of feedback controls on mixture because they're not trying to maintain one lambda. So they run them really more like a diesel, where we're controlling the fuel going in, and we're concerned about balance, and we're concerned about compensating for altitude and load, but we're not really concerned about stoichiometry. That's why when they gun a jet, you see all that black smoke out the tailpipe. That's rich. But yeah, certainly a lot of that technology from auto ends up in aeronautics. And there's a lot of aeronautic technology that has ended up in automotive. So there is a lot of sharing of technology. But we're trying to do, on a specific basis, we're trying to do some different things.
But there is no chance of the air pollution on the aeronautics?
Oh, there's tons of air pollution. Tons. They're cleaner than they used to be. But a lot, if we're looking at military aeronautics, they don't really care so much about pollution, especially in combat aircraft. Transportation aircraft's a different story. For the jets that we see fly in and out of, or like you were going to get onto, they've done two things with those. They've cleaned them up a lot from an emission standpoint. They've also cleaned them up a lot from a noise pollution standpoint. It always amazes me when I watch a movie from the 60s. You want to watch a jet land or take off in one of those movies, just look, aside from the noise, look at the amount of smoke coming out the tailpipe.
Yeah.
Or outside the turbine. So they run a lot cleaner than they used to, but they use some of the same thought processes, but some different technologies. So one of the thought processes they use is actually managing that fuel through the use of speed and load cells. So on a car, because we have a feedback system, we're constantly changing those. On aeronautics, it's all about base programming. What did I program it to do at this altitude with this much throttle, at this temperature, right? So the engineers do all the calculations and figure out, and that's why if it's having a problem, what do they have to do? Load new software, because the jet in and of itself can't learn the same way the automobile can, because it doesn't have the same type of feedback sensors. And will that change in the future? It probably will. Has it already? It might have. I don't follow up on that real closely.
Well, if they're sharing, that's a good thing.
That's always a good thing.
Yeah.
And there's a lot more money to invent things for a plane or a satellite than there is for cars. So a lot of that real expensive R&D starts out in industries where you have $1 million to put a satellite up in the air. And the satellite costs $5 million to build, right? They have some money there to try new technology. Once they perfect it, now it ends up in things like automobiles where we can really utilize it. So I'm going to talk about speed and load cells. That's our base programming that we use. And I'm going to talk about field trim, short-term field trim and long-term field trim. And I'm going to talk a little bit about sensor priority. And I'm not going to get all through this today, so we'll finish up on this tomorrow, and then we'll get it into the CDX chapter. But the PCM uses interaction or lookup tables, as they're commonly called. So how does the PCM make a decision on how to adjust the fuel, ignition timing, and when to turn on and off actuators? What comes into its programming? So the PCM is programmed from the factory with a series of mathematical algorithmic lookup tables. These lookup tables are similar to the multiplication tables you learned in grade school, only much more evolved. So many times when a engine has to be reflashed or reprogrammed, it's to change something in these lookup tables that the engineers didn't get correct the first time they did them. So we're going to talk about speed and load cells. And the speed is the speed of the engine, and the load comes from our load sensor, either our MAP or our MAF. So either our manifold absolute pressure sensor or my mass airflow sensor is my load sensor. My speed sensor is my cam and crank sensors or distributor. So using the multiplication table principle, let's build a simple cell table using just two inputs to determine the injector pulse width and the ignition timing for a specific theoretical engine. So obviously, normally more of this would be filled out and we'd have a lot more variances, but I just kind of want to go with the concept here. So as the throttle opens, more air enters the engine. The mass airflow sensor records the increase in air entering the engine. Based on the engine speed and the mass airflow reading load, the lookup table assigns preset commands for injector pulse width and timing, along with a lot of other things. This is overly simplified. I kind of want to go with the concept. So at 7 grams per second and 750 RPM, the engineers decided we want to turn the injector on for 1.8 milliseconds and put my base timing, or actually my timing period, at 8 degrees before top dead center. When I accelerate the engine to 1800 RPM, and I'm now flowing 18 grams per second of air into the engine, we decided I need a pulse width of 2.8 milliseconds and 15 degrees of ignition timing. When I further accelerate to 2500 RPM, and I now have 22 grams per second of air coming in the engine, we've decided I need 3.4 milliseconds of injector opening, and I need ignition timing of 23 degrees. So we can see as we move through these things, we're adjusting. So it's kind of like playing hopscotch as a kid. We jump from one of these cells to another. So as my conditions change, we instantly jump to that cell, which means my computer doesn't have to learn to react to the O2 sensor. It doesn't have to learn things. So the driving is a more seamless experience. Newer computers have more speed and load cells. So some early systems, I might have only had 32 of them. Newer systems, I might have over 1,000 of them. Because the more I can precisely put these different variables in, the better I can control it, the lower my emissions are going to be. So, and this is something if you're into tuning, or you've heard the term tuning, where people are tuning cars, what they're doing is they're breaking into these speed and load tables and changing the amount of fuel and the amount of timing, along with many other issues, given different engine inputs to change how the engine operates. Back up. So of course, there are many sensor inputs the PCM receives. The PCM, based on these inputs receives, has to find a matching cell or as close as possible. So obviously, the more cells I have, the better matches I'm going to get. Fewer cells, more, this is the best fit. It's close. So in the lookup table, the PCM issues output commands based on selected cell to operate the vehicle. So if I look here, oops. Where is, okay, it's just not playing quite right. So based on information, we ended up in this lookup cell based on our speed and load, and the PCM sends a command out to the computer and it says, hey, I want the injector for 3.01 milliseconds, fuel evaporation purge is off, torque converter is not locked up, I don't want any EGR, there's no reason to have the mill on. We don't need the fan right now. We're in closed loop, means we're looking at the O2 sensors. My fuel pump's on and my timing's at 13 degrees. So, you know, depending on which speed or load cell I'm in, EGR may be allowed to work or it may not be allowed to work. So we've actually had cars fail smog because someone put different tires on the car. Well, when they put different tires on the car, different size tires, it changed the speed and load cell and moved the speed and load cell that's operating on the dyno to a speed and load cell that doesn't allow EGR operation in the car failed smog. I've seen it where the wrong size tires or gear ratio changes cause a car not to run the OBD2 self-diagnostic monitors because we've moved to an incorrect speed and load cell. So these are really important for doing a lot of different things. So if we change something, even as simple as a tire size, it may affect which speed and load cell the computer chooses while we're operating the vehicle.
Different tire size as well as the different air level in the tire affect every percentage.
Yeah, everything is very sensitive. I mean, a lot of money goes into engineering these systems. And when we start playing with things, we don't always know what's fine, they allowed for that, and what's catastrophic or what causes a real weird problem. So that's why when I'm diagnosing a car, one of the things I do with my visual inspection is I look to see are there any aftermarket components on the car? In other words, has anything been changed on this vehicle to make it no longer stock? So not all sensors are equal in the eyes of the PCM. Some sensors have more say than others. If the engine is very cold, 20 degrees Fahrenheit, then the ECT sensor would have a great impact on my injector on time. If, however, the ECT sensor is reading 190 degrees Fahrenheit, then the ECT would have very little impact on my injector on time because that's just in my normal operating range. Yeah, that's nice. Go away. I don't care what you have to say right now. It's not important. So when we look at sensor priority, I can click through here. So I have my cam and crank, map, TPS, ECT, IAT, barometric pressure, system voltage, and my oxygen sensor picking up the rear. So this was traditional pre-1995, although there were some exceptions, and many early OBD2 vehicles up to 2000. The O2 sensor, if we read books, was considered a fine-tuning device, meaning it had very little control. What we found is that on these early vehicles, if all the other sensors are in normal operating range, it believes anything the O2 sensor has to tell it. However, if these other sensors are out of normal operating range, it'll believe them over the O2. It will not give the O2 sensor necessarily the ability to override it. And this really changed with OBD2. So the O2 sensor appears to have very little control. This is deceiving. If the sensors with higher priority are within normal operating range, then the O2 sensor has a great deal of control, enough to cause black smoke out the tailpipe or cause a vehicle to lose power and misfire from lack of fuel. The following slide shows sensor priority for modern vehicles and earlier vehicles when the higher priority sensors are in the normal operating range. So now we can see we have our speed sensor, our load sensor, and then our O2 sensor. And so it's going to take what it has for speed and load to develop to find what speed and load cell, and then it's going to look to the O2 sensor and go, did we get it right? And if we didn't, tell us so we can fix it. Then we put the other sensors after that. Now it needs to say, if I jump on the throttle and I go from idle to floored, the throttle position sensor has everybody's attention at that point. It's going to take over, but only for those couple of seconds that my foot's on the floor. So we can have changes for momentarily that will disrupt this because something has something really, really important to say. But under general operation, it's really all about the O2 sensor. We test the O2 sensor as part of our OBD self-diagnostic system. So once we prove it's working properly, we're going to believe anything it says because what we really care about is the emissions coming out the tailpipe. So the O2 sensor has been given much greater authority, and this is due largely to the increased need for lower tailpipe emissions, the implementation of the air-fuel ratio sensor, which allows a much wider range of fuel control and faster closed-loop operation. So in the old days with the zirconium sensor, I might not go into closed loop for 2 to 5 minutes. With air-fuel ratio sensors or wideband sensors, I'm normally in closed loop in 20 seconds now from when I start the car cold, which means now, even though I may not be running a stoichiometric, because it's 20 degrees outside, I'm able to control that fuel mixture. We've come a long way from a carburetor when we just had a choke plate that made the car run rich till it got hot. So we really want to help control those cold start emissions. And we actually have a cold start emission monitor on cars now starting in 2010 that actually monitors those emissions cold and evaluates how well we do and can actually set codes if we're not doing a good job. So on a 2005 vehicle, which sensor has the highest priority during closed loop operation when it comes to fuel control? Anybody?
On the 2005 vehicle?
2005 vehicle, highest priority sensor for closed loop operation when it comes to fuel control.
3.
3, the O2 sensor. It's all about the O2. That's why if I have a car that's running rich or a car that's running lean, or I'm wondering if the car is running rich or lean, the first place I go is go look at the O2 sensor. Because that's the computer's eyes. That's what it's seeing. That's what it's trying to make rich. So I may have a car that's running really, really rich, but if my O2 sensor says it's running lean, even though there's black smoke coming out the tailpipe, guess what? The O2 sensor is lying, and that's why it's running rich. So instead of wasting time with fuel pressure tests, testing injectors, looking for things leaking, let's see what the computer sees before we start second guessing the computer's decisions. Let me see what the computer sees. Let me look through the computer's eyes and see what the mixture looked like. And the computer's eyes are our O2 sensor. So the PCM, one of the advantages we have with cars is they're able to learn. And they store that learned into what's called an adaptive strategy. And that adaptive strategy is in our Keep Alive memory. That's why my computer has to get battery power all the time, because that's what powers up its Keep Alive memory. That's also why when I disconnect the battery, sometimes my car doesn't run quite right for a few blocks or a few miles. My transmission might feel funny for 20 miles or so. It's because we've erased the Keep Alive memory, or CAM, K-A-M, which is Ford's name for it. So this allows the computer to adapt to deteriorating conditions. So this is early computers, 1980 or 81, or even some Asian systems up into early 90s didn't have a Keep Alive memory. Every day was a brand new day. Every time you start the car, we're learning over. With OBD2, all cars have a Keep Alive memory. They have to, by law. So the program strategy allows the PCM to adapt to use abnormal inputs and still allow the vehicle to operate within normal service performance range, within reason. The CAM will maintain this learned strategy as long as it's supplied battery voltage. So as things get dirty, as things wear, this allows the computer to compensate for it so your car still drives great. But if I have a car that's adjusted for all these things and then it loses battery power and it goes back to the factory presets, it may not run good for a little bit. Very, very common. So sometimes people change the battery goes in and go, yeah, now my car runs really bad. You know what? Go drive it. Check for codes. If you don't have any codes, go drive the car. Let it relearn. Because even though your car is, 12 years old and got 160,000 miles, you just disconnect the battery. It's a brand new baby. It doesn't know anything. You have to give it a chance to relearn. So if I want to reset CAM, what I normally do is disconnect the battery. We don't have to install a new one. Driving the vehicle won't reset CAM. It'll learn CAM. It'll learn the adapters, but it doesn't reset anything. The only manufacturer you can use a scan tool to reset CAM is Ford. Everyone else in the world, I need to disconnect the battery. So if I ask you a question on, which of the following should be done to reset CAM, I'm looking for disconnect the battery. That's how we reset our Keep Alive memory, and we reset all of our adaptations. And that's true whether I'm working on an Asian vehicle or domestic vehicle or European vehicle.
Disconnect the battery.
Disconnect the battery. Normally, 2 minutes is fine. And we are at a good stopping point because the next thing I want to get into is fuel trim, which is going to take up a good hour to go through. And I don't want to just get into it a little bit and stop. So we're going to get into fuel trim tomorrow and actually see how that short and long-term fuel trim works and what a code like a P0171 for fuel trim at lean limit or a 172 fuel trim at rich limit actually are telling us, what they actually mean, and how we're going to go about diagnosing them. So I'm going to get into all that stuff tomorrow.